Hello everyone, I'm Aditi, presenting the project titled Unmasking Counterfeit Videos for the subject of neural networks on behalf of Team 4. Our problem statement is to identify or unmask deepfake videos from the real ones. Here is an example video clip taken from the YouTube, which shows Jimmy Fallon as Paul Rudd. AI synthesized media, which makes fake content look real by manipulation of digital images and videos, are known as deepfakes. They can be used for a number of malicious purposes, for example, a world leader confessing to illegal activities. Hence, it is very important to identify the fake videos from the real ones. We used the Kaggle's Deepfake Detection Challenge dataset for this project. The competition has separate training and testing sets. The test set has 400 videos. This test set is used by us as well. Thus, we set our baseline by comparing our results to the Kaggle's leaderboard. The training set has about 120,000 videos in the form of 50 compressed files, each of 10 GB. The training set, out of these 50 files, 40 files are used as training set, while the remaining as validation set. Fake video has a person's face morphed by another person. Hence, instead of using the video file as input to the model, we use the images in the form of facial crops as input to the neural network models. The Kaggle's dataset is not evenly distributed. The number of fake videos is 4 times more than the real ones. Hence, we sample 3 frames from the fake videos while 12 frames from the real ones. These are given as input to the YOLO face detection module. YOLO, which is an acronym for You Look Only Once, is a real-time object detector. It is fast as well as accurate because it contains 106 fully convolutional layer architecture. The face which is detected by YOLO is later cropped and stored in their respective folders. This gives rise to about 414,000 images as training set, which amounts to 2.5 GB of data and 50,000 validation images. These images are given as input to the classification models, that is the ResNeXt classifier, as well as the EfficientNet V6 attention classifier.
Hi, my name is Kenil Shah and I'm going to talk a little bit about the classification models that we have used as well as the architecture of our inference module. So our entire inference model has been divided into 3 serial steps. Given a video feed consisting of 300 frames, we first ran the YOLO face detection model on the first frame of video feed. So after this module, we will have the count of number of people present in the video as well as the bounding box for every person in the frame. Afterwards, we will initialize the tracking algorithm with the coordinates of this bounding box determined by the detection module. Now, this tracking algorithm would track the face over the entire set of 300 frames. Now, in order to reduce the runtime, rather than using every facial cropped image, we sample the frames with a sampling rate of 30. Thus, at the end of sampling and tracking layer, we will have a total of 30 face cropped images of every person in the video feed. We will use this set of 30 images as the input to both of our classifier. Thus, the classifier would have an output of size 30 for every person. We will take an average of these 30 values. Hence, after averaging both the classifiers, we will have n probability scores for n people present in the frame. Our algorithm would give a higher probability value if the video is fake. Now, if only one person in the video frame is fake, even then the entire video would be considered as fake. So, at the end, we would need only the maximum probability out of these n probabilities obtained. Lastly, we will take a weighted average from both the classifier and use that value in order to determine whether the video is fake or not. So these are all the steps that we discussed in the prior slides. So now comes the models that we have used. The first model that we have implemented is ResNeXt-101 architecture. As you can see in the image, we have just used the basic ResNeXt model with one added dense layer followed by a sigmoid function which would give us a probability score in between of 0 and 1. The model contains around 86 million parameters, and as you can see, it outperforms other state-of-art by 0.5%. It performs better than any other model by increasing the width of the model, that is cardinality of the model, rather than increasing just the depth of the model. Moreover, it also utilizes the strength of skip connection, which helps the model in avoiding vanishing gradient issue. So this is our second classifier. We have used EfficientNet V6 with an added attention layer for the purpose of solving this issue. So this family of models, which is known as efficient net, were introduced in around 2019 and caused a stir in the community as it had higher accuracy than any other model, but at the same time it used very few number of parameters. Instead of using just the base model, we added a set of 1 × 1 convolution layers to the base model. So now, as you can see in the image, at the end, we are multiplying feature maps with the attention maps and using that multiplied value and passing it to further FC layers, which is followed by a sigmoid function to give a probability score in between of 0 and 1.
Hello, I'm Shahil and I'm going to talk about the results that we achieved during this project. First, to select two classifiers for our ensemble method, we first trained 4 classifiers with base models as EfficientNet B6, ExceptionNet, EfficientNet B6 with attention layers, and ResNeXt-101. As we can see, EfficientNet B6 with attention layers and ResNeXt-101 models performed the best and had the best validation accuracy, and so we selected those models for our ensemble. Here we can see the EfficientNet B6 with attention layers, training and validation curves. Here we can see the training and validation curves for ResNeXt-101 model. We have analyzed the performance of our approach on a total of 400 videos present in Kaggle's test set by taking into account accuracy and log loss. We first needed to decide a threshold above which we would consider a video as fake. So from the plot, we can see that with a threshold of 0.5, we get the best accuracy on the test set. And so we considered 0.5 as our threshold value. Here, based on the threshold value of 0.5, we can see the classification report and confusion matrix. From the confusion matrix, we can see that 190 videos which were real were classified as real and 153 videos which were fake were classified as fake. Also, 49 videos which were fake were classified as real and 8 videos which were real were classified as fake. At the end, we achieved an accuracy score of 86.5% on the test set provided by Kaggle. To evaluate our approach with baseline techniques, we calculated the log loss obtained from the 400 videos. We obtained a log loss value of 0.371. The team at the top of the leaderboard has a log loss of 0.192. The log loss value 0.371 would have landed us to the rank of around 150, which is the top 7% on Kaggle's public leaderboard out of 2,500 participants. Thank you.